Hi, so I thought I'd vary it a little bit this week, rather than just email you, send you a video with a bit of a recap of what we did last week, and go through some of the questions, and then also set your work for this week. Well done to those of you who've been sending me the work so far, some really good work. Just please make sure that when you go through those past paper questions that you also check the mark schemes on the Moodle site, and you write down any points that you've missed in a different coloured pen, so then I can check quite easily that you've done all the work that I've set. Just a reminder, some of you still haven't sent me the précis of the secrets of the super elements documentary, so please make sure you do that. You should have also written up your Cornwall notes in neat, and remember you should have also done one of the questions. I think you had a choice of about 8, didn't you, from the Cornwall write-up, so you should have done one of those as well. So there's quite a bit of stuff there which you should have completed. So I'll say most of you are doing a really good job at sending me that. If you haven't been sending me that, please can you take pictures of the work that you've done and just email it to me, that would be great. So what I wanted to do today, obviously you can stop the video at any point, get your folders and files out. First thing I want to do is just go through some of the past paper questions that I set last week. So there were a few in your resource booklet. So one of the ones I wanted to go through is on page 33. So if you could find your resource booklet. And this was to do with why more energy is required if you're exploiting low-grade ores. Some of you are writing some very sort of general stuff, very generic stuff for this. The reason more energy is required for low-grade ores is that more processing is likely to be required. Also, if you're exploiting a lower-grade ore, you'll have to extract more material to get the same amount of a particular mineral out, so more rock will need to be mined, so more energy required, and also, as I said, more processing likely to be required, so hence more energy. So that was the question on page 33 that a few of you seem to struggle with a little bit. A little bit further on page 47 III, this is question 9A, to do with why it's difficult to recycle some used materials. It is quite important you kind of know the barriers to recycling. Lots of you have answered this quite well, and I can see quite a few of you have written down some of the extra points from the mark scheme. I just wanted to make sure you understood what, for example, thermoset plastics are. So I've just been logged off, so just bear with me a second. So thermoset plastics are plastics that can't basically be recycled, so you can't simply melt them down and then form them into something else. So certain materials just simply cannot be recycled. Another point which a lot of you wrote down from the mark scheme was this point of material identification, that often, for example in cars, a lot of materials are made of alloys where different metals have been mixed together, so unless those alloys have been labelled, it's difficult to identify what the materials are, and that makes it difficult to recycle them. And also, often when you recycle materials, the quality is lower, and so you can't often sell a recycled product. Good example being paper. When paper is recycled, you have to use quite a bit of virgin paper as well. If you just purely use the recycled paper, then it's very low quality, and then there's no market for the product. So that was that question on page 47 III. And then lastly, the question on page 49. Most of you seem to have got the idea of how to work out the reserve lifetime. Those figures in standard form using the powers, so it was 38.8 or rounded up to 39 years. I think everyone got that. For question B though, it says in 1992 the reserve lifetimes of many elements were similar to or even longer than those calculated in 1966. Explain the reasons for this. Well, there's lots of potential reasons, aren't there? First of all, there could be new discoveries of a particular mineral, so the reserve might increase. Now I think on the new spec they might want you to even talk about techniques that might be used to find those new minerals, or give specific examples. We've talked about nodules on the seabed, so maybe as technologies improve, it might be possible to extract those nodules and minerals on the seabed. That's going to increase the supply of minerals, which means they'll last for longer. The other thing that might happen, of course, is there could be changes in demand. So it might be that another material is used, so rather than using, for example, copper, people use plastics for pipes. That would mean the lifetime of copper will be longer. It could be that the demand decreases because people recycle more metals, and if a material is recycled, you don't need to mine as much fresh material again, so the mineral will last for longer. So those are some of the ideas for that question on page 49. Okay, so the topic for this week is soil. So we've finished all the mining stuff, so we're going to move on to soil. So if you want to put that as a title in your notes, and the first thing I want you to do is just to think about, so let me just find the Moodle site, is just to think about why soil is important. Now, we did do this right back at the very beginning of the lithosphere module. We talked about why minerals are important and why soil is important. So you might remember things like it's important as an anchor for roots, lots of nutrient cycling happens in soil, it's linked to food production, so lots and lots of reasons. So you could perhaps have a look back at your notes and just remind yourselves of why soil is important. Now, there's quite a nice PowerPoint on the Moodle site which I think you could start off with. It's called Introduction to Soil, and the first couple of slides, there's quite a nice video about the Dust Bowl. So the Dust Bowl is a really good example of how not to manage soils. So as you watch that video, if you could make a note of how they mismanage the soils and the impacts of that mismanagement, the environmental impacts, the social impacts, etc. So again, you can take a photo of that, and I can see that you've made your notes. Dust Bowl, it really is a classic example that you could use in the exam. The rest of that PowerPoint I think is relatively straightforward. There's another video to do with desertification, so again, just make some notes from that, and that's a nice kind of introduction to why soil is important and why you must manage it carefully. So the next part I'd like you to do is to think about the components of soil. I mean, what actually is soil? So this is going to work quite well as a spider diagram. If you've got A3 paper, that would be brilliant. If you haven't, then you could try to do it on A4. You just have to keep your writing quite small, but it does work quite well as a spider diagram if you like doing things like that. So I've actually got some soil which I've collected from the garden just to show you. So if you just bear with me a second, I'm just going to change the camera position. So just bear with me a second and I'll try to zoom in on that. Alright, so hopefully you can see just some sort of standard soil here that's collected from the garden. Obviously, if you were collecting a soil sample, you'd need to think about how you're going to standardise the method. So collected, say for example, the same depth, collected at the same time, because if you collected it on different times there might be different weather conditions, rain, different amounts of soil moisture. So also when you're collecting soil samples you have to standardise your method. So soil really is made up of a few different components. So one thing you can often look for in soil is the colour of the soil, and generally speaking the darker the colour of the soil, the more dead organic matter is present. So this is quite a rich soil, quite a dark coloured soil, so there's quite a lot of dead organic matter, and in fact you can actually see some bits of dead organic matter actually within the soil. So dead organic matter makes up one of the main parts of soil. The other thing that makes up soil is what's called the mineral skeleton. So the mineral skeleton is basically the weathered rock. So you can see a few examples here. There are a few little stones within this soil, and this is your mineral skeleton. Now some soils may have sort of larger grains, so things like sort of sandy soils. Some soils may have smaller sort of mineral grains, sort of clay soils, and some soils might be between the two, what you call sort of silt soils. So that's referring to something called soil texture. So soil texture is the sort of proportion of the different sized particles, the sand, the silt and the clay. Of course soil is made up of other things as well. Water would normally be present in soil, and water can be split into some different categories. You have things like, for example, hygroscopic water. Now hygroscopic water is the stuff sort of stuck to the soil particles. It's not actually available to plants. This is quite dry, it hasn't rained for several weeks, but you would get some hygroscopic water stuck to the soil particles. You also have what's called gravitational water, and that's water found within the soil that drains quite quickly through the soil, again often not available to plants. The really important water in soil is what's called capillary water. and that's water that's held within the soil that is available for plants to use. The other thing, of course, you'd find in soil would be the soil biota. Well, I'm sure if you looked under a microscope, you may well find soil biota within this soil. Almost certainly things like rotifers, and some of them are quite crazy looking creatures. We have talked before about dividing soil biota into different categories. I don't know if you remember the idea of decomposers and detritivores. It kind of neatly splits into those two, but there certainly would be some soil biota present within the soil as well. And of course air is found within soil, and air is very important because lots of the decomposition processes require oxygen. Lots of the soil biota aerobically respire, so having air in the soil is also really important. So hopefully that gives you kind of an idea of roughly what sort of soil is. So just bear with me a second and I'll just move the camera back again. Okay, so what I'd like you to do then, so on an A3 piece of paper, if you have one ideally, or you could maybe stick two A4 sheets of paper together, I'd like you to create a spider diagram. And in the centre of your spider diagram you could put the components of soil, and then on each of the arms on your spider diagram you could have the mineral skeleton or texture on one of the arms, air on another one, soil water, soil biota, and lastly dead organic matter. Now you can use your textbooks, and it's done very well in your textbook, page 129 through to about halfway down page 130, so you could use that to make your notes. So really just making notes on what those different characteristics of soil are. There's quite a lot of technical language in that which you'll start to notice. Things like mycorrhizal fungi, which are found within soil. Those are living things, are very important for soil fertility. So quite a lot of kind of new language to kind of get your head around. Things like PEDs, which are like the kind of shapes of the soil particles. So spend a bit of time kind of working your way through that and creating that spider diagram. Now there's also quite a nice PowerPoint on the Moodle site which you could use as well to help with that, called soil characteristics. And you'll see on the first slide of that the soil texture is often shown on a sort of triangular graph. It's a very odd kind of graph, but once you get your head around it, it's quite straightforward to read. So when you look at that soil triangle, you'll see you've got clay down one side, silt down the other side, and at the bottom you've got sand. And the way you read it is, if you imagine a point on that soil triangle, let's imagine a point right sort of in the centre. To read off the clay percentage, you go horizontally off to the left. To read the silt percentage, you go diagonally up to the right. And to read the sand percentage, you go diagonally down to the right. I will set you some questions on that on your homework for this week, and one of your tasks, and you can check that you're reading it correctly. Obviously, it has to add up to exactly 100, because all soils would be, those proportions, and I say it must add up to 100. Okay, so yeah, work your way through that PowerPoint. That's quite good. It's got some good stuff about particle size, talks about sandy soils and clay soils. When you've got the kind of perfect mixture of sand, silt and clay, it's called a loam soil, which is one of the most fertile soils. It's got a nice slide 5, about soil water, which I was talking about before, the hygroscopic water, capillary water, etc. And then it's got some really nice sections on the different types of soil biota, detritivores, wood lice. There's a nice video in there as well. So you could have a look through that. It does start to talk about pH as well, and soil structure, but I think that's probably, you could leave that for now, because I think that's going to be something next week maybe to write about when we start to talk about soil fertility and how humans can affect soil fertility. So that's going to take you, I don't know, maybe an hour or so, something like that, to complete those notes. Alright, now the second thing I'd like you to do is to write up the practical skills for soil. So for the exam you need to be familiar with the different ways in which you can measure the different components of soil. So in other words, how you can kind of compare soils from one location to another. And it's done again very well in your textbook. It's in the practical skills section at the back, which is on page 321 to page 323. Now, I don't really mind what format you use for this. It would work quite well with revision cards. You may or may not have those. You could again do it as a spider diagram. I'm quite happy for you to just do it as just sort of general notes is fine. I'll give you the main categories, and then you can obviously spend some time writing up the practical skills for these. So you need to know a method for working out soil texture, and there are a couple of techniques. One uses sieves, soil sieves, the other one uses the idea of sedimentation. You'll need to know the methods for working out the numbers of soil organisms, and that you'll actually find on page 320. You might remember things like Tulgren funnels and how to collect earthworms. We did that actually in the living environment module. You also need to know a method for calculating soil pH, and again there's two different techniques, a colorimetry, sort of colour change one, as well as one using a pH meter. Soil water content, so how you would calculate the percentage of soil moisture in a soil. That's quite a long method, and you've got to make sure you kind of write that up really precisely. And then lastly, how you would calculate the soil organic matter. The soil water content and the soil organic matter content kind of go together, because if you're working out the soil organic matter and you're weighing soils, you have to get rid of the water first. So it's a kind of two-stage process, that one. So again, you can write that one up. That's page, as I say, 321 to page 323 in your textbook. There is also a really good Moodle PowerPoint called a soil analysis, which you could also use to help you make your notes. It's got quite a few questions within that as well, so I would like you to try to answer those questions as you work your way through that PowerPoint. Again, you can take some photos of those. The first question, for example, says, when collecting soil samples from different sites, what precautions should be taken to ensure a fair test? Well, I've already talked about, haven't I, taking at the same time, same depth, for example. Also things like sealing your soil sample in a plastic bag so that any soil moisture doesn't evaporate, those types of things. So you can kind of work your way through that PowerPoint. It's got a nice section on soil texture. I'm just having a look through now. What else have we got on here? Soil organisms. It's got some quite nice questions about Tulgren funnels, for example, limitations of the techniques. Hopefully you would remember, again, if you could make notes on those, and again take a picture so I can see that you've done that. And it's got some stuff on soil pH, soil moisture, soil organic matter. Now ignore the exam questions on the last slide, because I'd like you to set you some specific ones to do this week. So hopefully that makes sense in terms of the notes and things that you need to be doing. So the exam questions I'd like you to do are as follows. So page 80, question B, and also page 81. So page 80, question B, and page 81 as well. Then page 88I, right the way through to 88V. There's quite a few different years of exam questions. Now you may not have the mark schemes for all of these on the Moodle site, so I will check. And if you haven't got all of the mark schemes, I'll make sure I email those to you at some point in the next day or two. Page 96I to page 97, and then lastly page 98. So there's quite a bit there to kind of work your way through. I think soil will probably take us maybe 2 weeks. So if I set you this task for this week and I set you another task for next week, that's probably the soil bit done. And then the only bit left on soil would be the soil fertility and how humans affect soil fertility. So there's some this week, some next week on soil fertility and how humans affect soil fertility, and then that's the soil bit pretty much done. The bit that's left on the lithosphere module is the nastiest bit of all, which is the biogeochemical cycles. The carbon cycle, phosphorus cycle, and the nitrogen cycle. Nitrogen cycle is the trickiest one. The carbon and phosphorus actually not too bad. That's probably going to take maybe another week, possibly another 2 weeks, and then that's the lithosphere module done. So I would hope that certainly by about the end of April, so the end of this month, lithosphere will be done, and then we've got the hydrosphere module to finish off. Alright, so unusual circumstances, aren't they? It's just really important to keep working your way through those notes, sending them to me so I can check them, and hopefully it won't have too much of an impact on things kind of when you sit your exams next summer, you sit your actual A-levels. Anyway, take care everyone, stay safe, and good luck with the work I've set.